Applying implicit differentiation at a single point in order to find the equation of a tangent line can be a little bit tricky. So in today's video, I wanted to show you the quick and easy way that you can use to find the equation of a tangent line to a curve at a given point. And I'm going to be showing you how to do this with an example. So let's go ahead and just jump right on into it. So the problem we're going to be going over is use implicit differentiation to find an equation of the tangent line to the curve at the given point. The curve that we have is x squared plus 2xy minus y squared plus x equals 2, and the point that we're given is 1, 2. So what you want to keep in mind when you're trying to find the equation of a tangent line to a curve at a given point is what the general form of the equation of a line has to look like. Any linear function or any line is going to look something like this. Y equals m times x minus x0 plus y0, where m is the slope of this line, and then x0, y0 is some point that this line goes through. So since it's already given that we know that the tangent line has to go through this point and be tangent to our curve at that point, we basically know right off the bat that x0 and y0 are going to be 1 and 2. x0 will be 1, y0 will be 2. But what we need to figure out now is the m, the slope. So in this general form of a line, m is going to be your slope, where x0, y0 is some point it goes through. So the slope, we need to figure that out by using implicit differentiation. Because when you use implicit differentiation, basically what that is going to be like is finding dy dx. Because dy dx represents the derivative of your function y with respect to x. So dy dx basically just tells you the change in y over the change in x, which is rise over run, which is exactly what the slope is. So what we need to do is use implicit differentiation to find dy dx using this equation. And then once we've done that, we can use that to figure out the slope that this tangent line needs to have. So basically we'll start by doing d dx of this full equation, both sides of the equation. So when we're finding the derivative with respect to x of both sides of this equation, I find it very helpful to first kind of write out and keep track of this over here, kind of on the side, just on the side of your page, and just leave it there basically as you go through this problem. Y is going to be a function, and x is going to be your variable. And we know this because we're taking the derivative with respect to x. Whatever you're taking the derivative with respect to, you're going to treat that as your variable, and then the other letter, in this case y, is going to be treated as a function of that variable. And the reason why this is important is because what that tells us is if you take the derivative with respect to x of your function, that is just going to be dy dx. We're not really going to be able to find the derivative of y other than to just say that it literally is the derivative with respect to x. However, if we take the derivative of x, that is going to behave the way we would expect it to. The derivative of x is just 1. If you have some term that you're taking the derivative of that only has x's in it and no y's, you can pretty much just take the derivative the way you normally would. Power rule, product rule, chain rule, quotient rule, whatever the case is, it's going to behave the way you would expect. But if something has a y in it, it's going to be a little different because y is its own function that's a part of that term. So you can see when we're taking the derivative here, we basically have these 4 separate terms, or I guess 5 separate terms if you count the other side of the equation as well. Some of them only have x's, which means the derivative of those terms are going to work the way we would expect. And then some of them have y's, which means we have to treat that as having a function as a part of that. But what that means is these terms that only have x's are going to be pretty easy to find the derivative of. So the derivative of x squared with respect to x, we're going to be able to find just using the power rule. So the power rule says we'll bring our power down in front and then lower our power by 1. So bringing the 2 down in front, lowering the power by 1 brings it down to a 1. So that just gives us 2x. Then to take the derivative of 2x times y, we're actually going to have to use the product rule because we have 2x as one thing being multiplied by y, which is another separate function. So to find the derivative of 2xy with respect to x, we're going to have to use the product rule. So the product rule says we're going to pick an f and a g. It doesn't really matter what you pick to be what. let's just go ahead and say 2x is going to be one function and then y is going to be the other function. Then you need to find the derivative of each of these things. So the derivative of 2x with respect to x is just going to be 2. And then the derivative of y with respect to x, like we said up here, is dy dx. And then product rule says basically that we'll multiply this one by this one and then add this one times this one. So 2 times y plus 2x times dy dx. So this here is the derivative of 2xy. So let's go ahead and take this up and bring it back over here. The derivative of 2xy, again, is just 2y plus 2x dy dx. And then what we're going to do is take the derivative of minus y squared, which is going to require the use of the chain rule because we have y is its own function now. So we have a function within a function. We have our function y all being raised up to the second power. So chain rule says we're going to take the derivative of our outside function, which is this squared piece here, which again is just going to be power rule. Bring the 2 down in front, leave our inside function the same. That's what chain rule tells us to do. And then we would again also have to lower the power by 1, which just leaves it as 2y. And then we have to multiply that by the derivative of our inside function. Well, our inside function is y. So the derivative of y is dy dx. And then the derivative of x, like we figured out over here, is just going to be 1. And then the derivative of the right side of our equation is just a constant. So the derivative of a constant is always 0. So now that we've taken the derivative of both sides of our equation, what we want to do is move our dy dx terms over to one side of the equation and then move our non-dy dx terms over to the other side. All of our dy dx terms are already on the left side of the equation, so we can basically just move the rest of these terms over to the other side of the equation. So we'll keep our dy dx terms here. And then to move these other non-dy dx terms over to the other side of the equation, we can basically just subtract them all from both sides of the equation, which would cancel them out on the left and then bring the negative version of them over to the right. And hey, do me a favor, if you're getting some value out of this video, please go ahead and hit that like button down below. And while you're down there, go ahead and hit that subscribe button as well so you're notified of all my new videos that come out. We'll keep crushing it all term long in calculus together. But let's go ahead and continue on with this problem. So now that we have our dy dx terms on the same side, what we can actually do is factor out dy dx from that side of the equation. So now if you take a dy dx out of this term, you're just going to be left with 2x. And then if you take dy dx out of this term, you're just going to be left with minus 2y. And the reason why that was such a great thing to be able to do is look at what we have now. We have this equation which only has a single dy dx in it. There's only one of them. And the reason why that's so great is we can get it all by itself now and actually solve for it. To do that, since we just have dy dx times all this stuff in the parentheses, all we have to do is divide the stuff in the parentheses over to the other side of the equation. So that's basically just going to give us dy dx equaling the whole other side of the equation divided by what's in the parentheses here. So remember what dy dx represents. It represents the slope of our curve that we were given initially, this x squared plus 2xy minus y squared plus x equals 2. This is the curve that we were trying to find the tangent line equation at a given point. Well, this dy dx just tells us whatever the slope of this initial curve is for whatever x and y values we plug in here. So if we want to find the slope of the tangent line at the point 1, 2, to do that we would just have to plug in 1 for x and 2 for y into this dy dx equation, and that'll tell us the slope. So we'll just put in 1 for x and 2 for y. To find the slope of our curve at the point x equals 1, y equals 2. And doing that is going to give us 7 halves. So basically that means that the slope of our tangent line equation has to be 7 halves, and then we already know that x0 and y0 is going to be 1 and 2. So basically we can just go back to this tangent line equation, plug in 7/2 for m, 1 for x0, and 2 for y0. So doing that is going to give us y equals 7/2 x minus 1 plus 2. And then we can just simplify that. So if we distribute the 7/2, and then we can combine our like terms, minus 7/2 plus 4/2 essentially is negative 3/2. So that gives us y equals 7/2 x minus 3/2, and that's going to be the equation of the tangent line to that given curve at the given point. Hopefully you found this video helpful. If you did, please be sure to hit that like button down below and the subscribe button as well with that bell icon. Don't let YouTube decide which topics you get to learn about. Make sure you subscribe so you can check back for all my videos, and together we'll keep crushing it all term in calculus. If you want to learn more about implicit differentiation, go ahead and click on one of those videos over there. Thanks, and see you next time.